Hi. So we're going to solve the second question now. The question says that the 3-meter long ladder weighing 20 kg. So let us first, as the previous question, let us first draw the ladder. Okay, I'm sorry. I don't have that good thing over here. So I'm making the ladder like this. I'm going to make the wall and the floor first, and then I'm going to join that as a ladder. Okay, so that's my wall, that's my floor, and that's I'm saying that my ladder goes like this. Okay, I'm marking them A and B as my ladder. It says it's a 3-meter long. So given AB is 3 meter. Okay, let me make this C, and this is 90 degree. Of course, it is wall and the floor. Now, first force acting on it is its weight. It says 30 kg. I'm saying that is the center of it. Let us mark it as D. And I am saying the force acting on it is 20 kg F. Okay, so let's mark it. I'm calling it W. And let me just write it down. Given W is 20 into 9.8, which is 196 Newton. Done. Now let us go ahead. Leans on a frictionless wall. So wall is not giving any friction, but there, as it is touching here, there is some reaction force. Let me just mark it R. Okay, I'm sorry. It is different from your figure because it's a reaction force. That's why I'm marking it, and it's easier for you to understand. I have written R is question mark. Its feet rest on the floor 1 meter from the wall. So given AC is 1 meter, and it does not say frictionless, so there has to be some friction. If the ladder is like this, it is tend to slip outside. So where would be the friction acting? Inside. So I mark my frictional force here, and let me mark it small f. Okay, is that clear? I have no idea how much this frictional force is. Okay, so that's again F is equal to question mark. Now there is some reaction force here also. I mark it as some force. Let me mark it capital F. Okay, so this is my capital F. I hope there is no confusion. Small f, frictional force, capital F, reaction force at B. Now, it says find the reaction forces of the wall and the floor. So what's my aim is to find reaction force of the floor and reaction force of the wall. These two things I have to find it out. Now, again, same as we have done in the previous question, my ladder is not moving anywhere. It is in equilibrium. So it will have translational as well as rotational equilibrium. Let's first talk about the translational equilibrium. So what I can say is my ladder going up or down? No. So all the forces acting upwards are equal to all the forces acting downwards. Can I say my F is equal to W? Is that right? And if it is not going left and right, I can say my reaction force of the wall is equal to the frictional force. Now, that was all about my translational equilibrium. Now, let us talk about the rotational equilibrium. Or maybe we can just put the values over here. So for clearly, I can say that my F is equal to 196 Newton. And I don't know R, I don't know F. Okay, so now for that, let us go to the next one. Okay, by the way, we haven't marked it here. This is 1 meter. This is 3 meter. Can you just tell me the BC? Now we are right now working for the rotational equilibrium. For that, let us just first look at the triangle ABC. In triangle ABC, BC square plus AC square is equal to AB square. This implies that BC is equal to under root of 3 ka square minus 1 ka square. That is equal to 4 minus 9 minus 1. That is root 8. 4 into 2. That is 2 root 2 centimeter. Okay, because we would need that value. Now, rotational equilibrium में बेटा आप कोई सा भी point ले सकते हो, but I will try and take a point on which the maximum forces are acting so that I don't have to make the number of components more. I just took point A because यहाँ पे F भी है normal force और यहाँ पे small f भी है frictional force. So I just let it be there. Now I see now there are two forces. One is D, which direction it is trying to move it in. As I could see, it's here. It is trying to move it in the clockwise direction. I look at the perpendicular distance of R, which is this, and it is trying to move it in the anti-clockwise direction. So what do we mention here? In equilibrium, anti-clockwise moment is equal to sum of, here only one is there, is equal to sum of clockwise moment. Anti-clockwise, I have R. So what is the perpendicular distance between A and R? This dotted line, which is equal to BC, which is 2 root 2. Okay, so what do I say? R into 2 root 2 is equal to, now this is trying to move it in the clockwise direction, so which is W, and now the distance is half of AC because it is acting at the center. So can I call it 0.5? So I call it W into 0.5. So the value of R comes out to be W, which is 196 Newton into 0.5 divided by 2 root 2. And once I solve all of them, I get 34.65 Newton. So the reaction force on the wall is this, and the reaction force on the floor, which is the normal at the floor, is 196 Newton. Okay, do not get confused by the answer given in the one. What they have done, they have now taken out the resultant of these two. Okay, so how you can calculate? You can find out the value for the resultant by small f, which is R, which we have calculated, and capital F, which is there, it's the W. But here it talks about the normal. You can simply say F and R, which the answer is 196 Newton and 34.65 Newton. I hope it's clear for you.